All right, good afternoon, chemistry class. Today we're going to talk about the ideal gas law. Now, in your notebook, you want to open up to page 11 and go ahead and copy down the combined gas law. This time I'm including the variable N. Remember what N represents? It represents the number of moles. And so from the combined gas law, we get P1 times V1 over N1 times T1 equals P2 times V2 over N2 times T2. And again, we just inserted the N on the bottom there. And it says at STP equals 0 degrees Celsius. So what would that be in Kelvin? Well, you just add 273. So that's 273 Kelvin. And then the one risk should say 1 atmosphere. So I'm going to switch over and I'm going to show you how we take the combined gas law, and from the combined gas law, we can come up with what's known as the ideal gas law. So copy this down in your notebook and we'll be ready to talk more about it in class. So again, what you have here is your combined gas law, P1 times V1 over now N1 T1 equals to P2 V2 over N2 T2, okay? Now let's suppose we took this side and let's suppose that this is at STP. So what is the pressure at STP? Well, that's 1 atmosphere, all right? And then we could say that if we have a 1 mole of a gas, then the volume would be 22.4 liters per what? 1 mole. So there's our N. And then our temperature would be 0 degrees Celsius, which of course we said is 273 K. All right, so grab your calculator. If you don't have one, pause the video. Go grab your calculator. Okay, so that's going to be equal to what? Well, now we're just going to drop the twos because now we just have pressure, volume, we have the number of moles, and we have temperature. And over here, we've already placed those. So take your calculator, and essentially what you're going to do is 1 times 22.4 divided by 1 divided by 273. All right, you do that in your calculator, what do you get? Well, you get 0.0821. And what's going to be the units? Well, usually it's expressed like this: liter atmospheres over mole kelvins, just like that. Now, this on this side of the equation is known as the ideal gas constant. And we use the letter R to represent the ideal gas constant. And so if we just complete this, put our PV over NT, and now we have the ideal gas constant. Actually, I should put it as right there. And that's just the unit for that. So if we go back and we then substitute R, we could say R is equal to what? PV over NT. And if we rearrange this equation, we can rewrite it as PV equals to nRT. And usually this is the form that you're going to see it in. And this is known as the ideal gas equation. And sometimes you'll hear it called PERV-NERT, PV equals nRT. Now, you could also write it in this form, or you could solve for any of the variables that you wanted to. Now, the important thing about the ideal gas law is that you must have the correct units. And when you're using the constant of 0.0821 for your R, then that means that pressure must be in the units of atmospheres, that volume must be in the units of liters, that your N must be in the units of moles, and that your T must be in the unit of kelvins. All right. So you need to make sure that you're in these units. It must be in these units. Now, some textbooks that you go to will use a different value for R. For example, if they use kilopascals, then they would have a different value of R because you would have 101.3 kilopascals times 22.4 divided by 273. And that would give you a different value of R. So jot this down in your notebook and let's do a couple of these problems together. All right, going back to my slides here. All right, so here we go again. P is pressure, V is volume, N is your number of moles, R is your gas solid constant, and T is your temperature. And again, pressure is in atmosphere, volume's in liters, N is number of moles, T is kelvins, and R is our ideal gas solid constant, 0.0821 liters atmospheres over mole kelvins. And so you want to memorize that constant and memorize that formula. All right, here's an example. Take a moment, jot this example down. You may need to pause the video and then restart it, and we will solve this one together. All right, so you've got the problem here. It says a diver's tank has a volume of 21 liters at 15 degrees Celsius and a pressure of 3.1 atmospheres. How many moles of air is in this tank? Let me switch over here to our paper. So what we have here is we've got a diver's tank. Okay, kind of looks like one of these cylinder type things like that. It's got a little valve up here and so forth on that valve. We know that the volume of this is 21 liters. Okay. We know then that the temperature is 15 degrees Celsius. So we add 273 to that and we get 288 kelvins. We know that the pressure inside of here is 3.1 atmospheres. And then what we want to try to do is we want to try to figure out the number of moles. So that's N. So we're going to use our ideal gas solid, PV equals to nRT. We plug in our P, it's in atmosphere, so that's good. We don't need to change anything. That's 3.1. We plug in our volume, it's in liters, so we don't have to convert that to anything. We have our N. Well, N is our unknown. R, what's R? Oh, yeah, that's that ideal gas constant. So that's 0.0821. And then times the temperature, which is 288. All right. Shift this over a little bit here. Okay. So now we want to solve for N. So we're going to say N is equal to 3.1 times 21. Whoops, that's supposed to be parentheses, over 0.0821 over 288. All right. So in your calculator, you're going to punch in 3.1 times 21, then divided by 0.0821 and divided by 288. Again, be sure that you hit divided by again down here. Don't hit times. It's on the bottom, so you must divide it as well. All right, what did you get in your calculator? All right, well, hopefully you got 2.75. And what should be the unit with that? Well, that unit is moles. Okay, if you go back, all the other units will cancel out. It kind of gets a little bit messy, but all the units do cancel out, and you would have moles. All right, let's go to our next problem on our slide here. Oops. Okay, let's go to this one. Example number 2. All right, pause the video and copy this down. All right, so it says a small tire is filled with oxygen gas and has a volume of 3,150 milliliters with a pressure of 925 millimeters of mercury. The mass of oxygen is 15.8 grams. What is the temperature of the tire? All right, so kind of got a little bit of an odd situation here. I don't know why you fill a tire up with just completely oxygen, but it works because we've got to do a couple things here. So here's our tire. We got a little small tire. All right. And what do we say the conditions were? Well, we said the volume of this tire is 3,150 milliliters. We said the pressure of this tire is 925 millimeters of mercury. All right. And then the mass of our O2. Mass of O2 was 15.8 grams. All right, so we got to do a couple conversions here, all right? We need to, first of all, convert milliliters to liters, okay? So remember, if we do our T-chart, milliliters go to the bottom. So we're going to have 1,000 milliliters, and we're going to have 1 liter on the top. So we're dividing by 1,000, okay? So what's that going to do? Well, that's just going to move our decimal place over 3 places to the left. So that's 3.150 liters. All right, we've got to convert 925 millimeters of mercury. So let's go ahead and convert that over. We'll put millimeters of mercury on the bottom. And we know then that there are 1 atmosphere equals to 760 millimeters of mercury. All right, so we take our calculator, we take 925 divided by 760, and you should get like 1.22 atmospheres. All right. Now this one, 15.8 grams of O2, we're going to convert that over to moles of O2. So we're going to put grams of O2 down here, moles of O2 up there. Remember how to do grams and moles? What do we need to know? Molar mass. So it's O2, so that means you got oxygen times 2. So 16 times 2 gives you 32.0. And so we'll take 15.8 divided by 32, and we'll get 0.490 moles. So now we've got our volume, we've got our pressure in atmosphere, and we've got our number of moles. So we're going to say PV equals to nRT. And what are we trying to find out? Well, we're trying to find what is the temperature in this. So we're going to solve for T. So our pressure is 1.22. We'll multiply that times the volume, which is 3.150, times our N. Okay, well, that's our moles. So that's 0.490 times our gas law constant, 0.0821. You need to get that memorized. And then we're trying to find T. Okay, so then what are we going to do? Well, we're going to solve for T. We're going to divide both sides by 0.49 and 0.0821. So that's going to give us T equals 1.22 times 3.150 over 0.490 over 0.0821. So we get our calculator, multiply the top, divide by the bottom, and you should come up with like 96.3 kelvins. All right. So make sure you get that in your calculator. If you didn't, go back through it, see what you did wrong. Now, that would be okay unless it asks you for degrees Celsius, which is probably what we'd want to do. And so to convert this over to degrees Celsius, what do? Well, instead of adding, we subtract 273. So when we take 96.3 minus 273, we actually get a temperature of a really, really cold temperature, negative 167 degrees Celsius. So that's pretty cold. And I would accept either one of these temperatures here, unless the problem just specifically asks you for degrees Celsius. But again, it's a good idea to go ahead and put it in degrees Celsius. Not a real realistic problem, but it does illustrate how to do some of these PERV-NERV, these ideal gas law problems. So we'll work some more problems in class and do some more practice with this, and then we'll talk about some deviations from your ideal gases and how they differ from what real gases actually are. All right, look forward to seeing you next time in class.